Hi, my name is Jamie Ledbetter. I am the Biosystems Engineer and Team Lead for AQUABOT's Team 26061.
Hi, I'm John. I'm Electrical Engineer.
Hi, I'm Alex. I'm Aerospace Engineer.
Hi, I'm Myra, and I'm the Optical Engineer.
I'm Pablo, the Mechanical Engineer.
I'm Robert, and I'm also an Aerospace Engineer.
The ocean is a rapidly changing environment due to factors like global warming, natural disasters, and pollution. These impact marine ecosystems and create challenges for effective monitoring and response. In scenarios like pollution events or marine emergencies, real-time data is critical. However, current monitoring solutions are often expensive and difficult to scale. Our solution is an affordable, autonomous aquatic drone swarm designed for surveillance and environmental data collection in the ocean or other large water bodies. The swarm actively relays telemetry data, information on key water parameters, and live video back to the user from any location with satellite connection. This year, our goal was to build on previous designs and develop a fully integrated, ready-to-use system capable of rapid response and continuous environmental monitoring.
The AQUABOT Swarm is a scalable system of drones, each equipped with a pH, temperature, and salinity sensor, with the main drone also equipped with a camera. The main drone communicates to the ground station using Starlink, making it controllable from anywhere in the world, while it communicates with the other drones in the swarm using the ESP Now Wi-Fi. The key objective for this project is to collect critical marine data such as pH, conductivity, and temperature, to get live stream video from the drone in 1080p, to have swarm movement of at least 3 drones, and to have a scalable platform where we can add more drones if needed.
Here is the system block diagram for the main hull for AQUABOT. As you can see, it shows all the components, major components and subcomponents for the project. It shows the most important things, which really are the connection from the ground station to the hull, and then the subcomponents within the hull that control things like the rudder, the motor, all the sensors and data collection, as well as where the power goes. And so this is kind of the one-stop shop for this project.
One of our featured components is the ground station with a live video stream and real-time environmental data, as well as a GEO overlay for monitoring and mission control.
Here we show our graphical user interface GUI, which is the main way a user interacts with the AQUABOT system. In the right, we display the live video feed from the onboard camera in real time. On the left side, we have our geo overlay, which includes environmental data like temperature, pH, salinity, and position data from the PICSOC. In this demonstration, Eddie is accessing the GUI remotely from Ireland, showing the ability for global operation. While the system is running, both the video and telemetry are displayed live and recorded directly onto the Jetson, ensuring all data is synchronized for later analysis. The demo focuses on remote monitoring and data collection, but the GUI is also designed to support navigation and control features, which are currently being integrated into the full system.
Another key feature of our drone is its self-righting, waterproof, and impact-resistant design. In this video, you can see us testing the self-righting abilities of our hull by twisting it over in the water and making sure it lands upright. The final component of our system is our electronics and communication systems, which include a Starlink, a Jetson Nano, and an ESP32.
Here we can see the main electrical components of the AQUABOT. These include the safety kill switch, the Starlink, the Jetson Nano, as well as all the electrical components that ensure every component is receiving the correct voltage. Underneath this is the motor, as well as the servos. Here we have the propulsion system. In the top image we can see the rudder and propeller, which was custom designed for the geometry of this hull and 3D printed out of carbon fiber reinforced ABS, similar to the motor mount in the lower picture. This connects the motor to the shaft using the CNC'd stainless steel flange. In the right image we can see the motor cords which connect to the ESC, as well as the rudder servo and servo mount. Both of these components connect to the PICSOC for autonomous Here we have the successful propulsion system GUI test. It starts with an arming sequence which is completed in the GUI, where waypoints are added, uploaded to the PICSOC, and the mission is launched. As you can see in this video, the motor spins up to cruising speed of 2.5 miles per hour, and the rudder orients itself autonomously to navigate to the nearest waypoint.
This is the RC boat. This is a smaller portion of the project. This demonstrates, these demonstrate really the swarm control aspect of the project, the inter-drone communication. It shows that all of the data monitoring and drone monitoring systems are good, as shown in the graphic on the right. It shows that the flight controllers are working well and that all of the drones can work together as one piece to solve this problem.
The AQUABOT sensor package includes 3 different sensors: a pH probe, a temperature probe, and a conductivity probe, all of which are connected to an ESP32, which allows the data to be output as a CSV file, before being passed through our Jetson Nano and Starlink, and finally to our ground station GUI, where the data is accessible by the user right beneath our GEO overlay.
And here we show our final water demonstration on the lake. During this test, our main focus was to validate waypoint navigation, ensuring that the system was fully waterproof. The AQUABOT was able to operate on the water without any leakage, confirming the integrity of the enclosures. We also verified connectivity using Starlink, allowing the system to maintain communication during operation. While the system performed successfully, we identified further calibration is still needed to improve navigation accuracy and overall performance.
Final steps for this project include dialing in the rudder control for proper navigation to waypoints, mounting the sensors to the hull, and incorporating RC boats into swarm navigation.
Last but not least, we would like to thank our sponsors, Eddie Stalker and Dr. Marvin Slepian, as well as our mentor, Jim Sweetman, and the University of Arizona College of Engineering.